Hello, everyone, and welcome to the Semiconductor Industry Association's public webinar series, where we address key issues facing the semiconductor industry and the semiconductor market. My name is David Isaacs, and I'm the Vice President of Government Affairs with SIA, and I'm here to introduce today's webinar. Today's webinar is the fifth and final episode of the Decadal Plan for Semiconductors webinar series. The Decadal Plan is a joint collaboration between SIA and the Semiconductor Research Corporation that identifies significant trends and challenges facing the semiconductor industry and semiconductor technology in the coming decade. During previous webinars, we discussed new challenges facing semiconductors with regard to energy efficiency, analog electronics, ICT security and privacy, and communications. And today we will be focusing on memory and storage. As we all know, the amount of data we create is rising exponentially. In 2020 alone, more than 59 zettabytes of data were produced and consumed. And storing this enormous amount of data and ensuring energy efficiency and preventing market failure is critical to today's computing systems. So the main goal of today's webinar is to identify the research agenda for semiconductors to discover new approaches to memory and storage. We have a great group of panelists for the webinar, and to get things started, let me introduce Sean Eiler of Micron Technology. With that, let me turn it over to Sean. Thank you.
All right, thank you, David. So you can see we've assembled an elite group of panelists here. It's actually been a real pleasure to work with many of these people over the past year as we've been going through this Decadal Plan activity where we explore the future of the semiconductor industry. Next slide, please. I'm a little bit about myself. I'm a Micron fellow. I've been in the industry for 30 years now as of last month. My career has been focused on product development, design, and architecture activities, all entirely in the memory industry, starting with EEPROM and moving to NOR and now DRAM and NAND and emerging memories. For the past 10 years or so, I've been leading a team that does systems research. And so this Decadal Plan work has been very exciting for me as it really looks to the future of systems. Outside my career, I enjoy many outdoor sports and many family activities. You can see I'm working from the Yosemite Micron office today. Next slide, please. Overall, the theme of the Decadal Plan for semiconductors is to look forward to the 2030 timeframe with an eye towards information and communication technology research goals. And this drives research through SRC and SIA, as well as to some degree funding for research activities. The fact of the matter is that hardware and software paradigms today in the industry are really changing. And they're changing due to the fact that scaling in many areas is either becoming more expensive or is starting to slow. And also because of the fact that many application owners are inspired now to introduce their own domain-specific accelerators into systems to accelerate their specific applications in a very function-specific way. And so we've identified that it's really important to identify these trends moving forward, understand the roadblocks and challenges of the industry, and then once those are understood, support the strategic visions of semiconductor companies, put a stake in the ground to figure out maybe a starting point for what's best and the right path forward for this research. And then guide those research programs through the next 10 years. The future really can't wait for this, and because of that, we're bringing the best minds together to achieve some of these goals that today seem unimaginable. Next slide, please. Here's an overview of the companies that have been involved with this. It's been a real pleasure to work with the thought leaders from the industry that come from this really diverse set of backgrounds. Next slide, please. Okay, in the Decadal Plan, there are 5 seismic shifts that were identified. Today, we're discussing the growth of memory and storage. And so here, the grand goals for memory and storage are really centered around delivering both capacity and energy efficient operation of both of these technologies. There's no doubt that it's a big challenge to expand anything by 100x. And so clearly, we're looking forward to new technologies that will make this happen. Energy efficiency oftentimes is, as you'll see, as you've seen in other webinars, I'm sure, energy is one of the limiting factors that limits compute, what we can do with compute moving forward. To the extent that you know, if we scale on a linear trajectory, then it's very likely that we will exceed the world's energy production in the consumption of our data centers. And so on the one hand, we think of energy efficiency as not needing to increase the world's output of energy. But on the other hand, energy efficiency really can come be realized in the added bandwidth that we can get out of memory and storage systems. And so we'll talk about that a bit more today. So again, the grand goals of the memory and storage really are centered around reducing cost and increasing capacity, and increasing performance of those systems. Next slide, please. Some key findings from the Decadal Plan. Number one, society's production and use of data and information is absolutely exploding. You know, we've seen this, you know, for thousands of years. We've been increasing the amount of information that we store as a society, and increasing as the amount that we store as a function of per capita in society. But recently, I'd say we much more make use of the data, the stored data. It's no longer going and looking things up in an encyclopedia. Now you Google things, but that's kind of the thing of the past as well. In today's environment, now we're building big models based on what's stored in this enormous wealth of data that we have stored. And then we use those models to run inference on the data that we have stored. The committee has identified several key limits to the future of compute. One of them, as has been discussed many times, is energy. Also, believe it or not, silicon wafer supply. There's a limited supply of pure silicon that's conducive to silicon production. And you know, and people are starting to look now at recycling. Sorry, we have somebody who needs to mute, please. The silicon wafer supply is going to be a challenge in the next decade, and people are starting to look at recycling effort to maintain that continuous supply of pure silicon. Memory and storage capacity is clearly a limiting factor moving forward. We're producing data at a rate that makes it very, very difficult to store and more importantly, get results from the stored data that we have. Memory bandwidth is a really big deal as people move to domain-specific accelerators. All of these domain-specific accelerators largely are bandwidth hungry, and so memory bandwidth is a very big deal for 2 reasons. First, for the domain-specific accelerators, but also because when we introduce those accelerators, they increase pressure on the memory and storage system, but also sometimes that memory bandwidth can be used to offset the need for storage bandwidth, because we can do caching in memory, et cetera. And then these increased bandwidth requirements, in addition to the overall sort of macroeconomic view of energy, there's a thermal issues involved in transferring data local to a processor or a domain-specific accelerator, and at high bandwidth, now the energy consumed in that causes thermal problems, and we have thermal issues to manage. So all of this put together leads us with some really big challenges as we move forward. Next slide, please. This is just a view of for the past 2,000 years, the increase in information. And you can see, they're not often that we see axes that have, 24 orders of magnitude or 10 orders of magnitude on the y-axis. This is a really big explosion. And as you can see, much of that explosion has happened within the past, decade or two. And so looking forward to the next decade, I think we can expect to see some things that are really compellingly different than what we've seen in the past. So society is increasingly shaped by this stored information, in that we store the information and then make use of it in very interesting and creative ways. Next slide, please. A comment on memory bandwidth. So if you look across my history in the industry, back in the 90s, the memory systems were built basically one memory cycle per processor cycle, believe it or not. And they were single core computers that were being built in the 90s. As we've moved forward, we've moved into more multi-core systems and more recently over the past decade or so into domain-specific accelerators. And we're seeing these domain-specific accelerators occur in data centers, for example, in the TPU that you see in Google's data center. You see your phone, your iPhone or your Samsung phone has many domain-specific accelerators in there because the focus is on energy efficiency of those operations. One thing that's really important to note is that while latency lags compute by a decade per decade, that's a big deal for these applications that are sort of serially oriented, where you can't parallelize anything. It's just a matter of chasing pointers through the memory. Your overall latency doesn't increase as fast as you would like it to, perhaps. But the bandwidth also is lagging compute by a half decade per decade. And bandwidth is we can throw more and more parallelism at bandwidth, but very quickly that starts to run out of steam. And that's particularly amplified now. The bandwidth problem in particular is amplified by the fact that now all these domain-specific accelerators are being introduced. So there's an industry need to alleviate these memory bandwidth challenges and to do it in a very, very energy efficient way, especially as we move into this domain of specialized accelerators. Next slide, please. This is a little bit of repeat of what was on the slide two slides ago, but as viewed by the storage industry, now you can see when we go to put all this data someplace, it doesn't just fall off the edge of the earth. All of this data that we create ends up getting stored someplace and kept for a long time. And it used to be that data was just stored, and it got colder and colder and colder. But the key thing that I've noticed recently is that the society now is embracing the use of that cold data, and they'd like it to be warm data because they want to browse that entire data set to build models from that data, train those models, and then run inference against that data set again to draw patterns, draw social networks, draw relationships out of that data. I think as we move forward, we're going to see that more and more, and having all of this data in one place where we can do that is an incredible advance for society. Next slide, please. So I'd like to introduce this view of the memory landscape. And in the memory landscape, there are a few parameters that are really important. One is bandwidth, another is latency, and the third is capacity or cost. We can kind of use the words capacity and cost interchangeably in a way, because at some point you have a fixed amount of money that you can spend for memory, and so that will limit the overall capacity. And on this graph, we're showing the x-axis is latency, the y-axis is bandwidth, and then each bubble represents a memory technology. and the size of the bubble represents the capacity or the inverse of the cost of that memory. So a cheap memory is shown in the green circle with a large bubble. Expensive memory is a smaller bubble. Fast memories are in the upper left. Slow memories are in the lower right. But we could have a very slow, a high bandwidth memory that would sit in the upper right-hand corner, for example. And so all of these are important parameters. I'm going to walk you through a progression of how the memory industry has changed over my career, and over the next few slides. Next slide, please. So if we map memory and storage onto this, then you can see memory tends to sit on the left, the upper left, in fact, side of this graph. And what I've learned through driving, evangelizing chalcogenide-based emerging memories in the industry for a large part of my career, I've learned that there are deeply ingrained paradigms of how people think about memory and storage. Memory is thought of as being fast and volatile. Storage is thought of as being slow and persistent. And all of the architecture of all of the systems that interface to those tend to follow those paradigms. And there's some shift over the past 5 to 10 years of this in the introduction of persistent memory and to some degree byte addressable storage. But overall, I think we tend to see storage tends to be to the right and memory and with large bubbles, and memory tends to be to the left with much smaller bubbles. Next slide, please. The industry for most of my career was in the blue and gray circles here, and there was a really interesting radical innovation in the DRAM world, in the introduction of HBM, and at the same time a competing standard which is very similar, that was HMC. And so the change there is that we made use of through silicon via 3D integration of DRAM to put multiple memory layers on top of a base IO die. And the interface now to that, since it was much higher capacity, it wanted a much higher bandwidth interface. And so with that, the architecture was chosen to put that on a silicon interposer adjacent to the ASIC, and then give a high bandwidth connection to this stack of DRAM. So you can see that where we had 100 gigabytes or so maybe in a DIMM on a server. Now we move to this HBM model where we only have 8 gigabytes now, more recent ones moving to 16 and 32 gigabytes, but it's much higher bandwidth, but it's limited. The form factor naturally limits it in capacity. And this is a trade-off now that we're seeing is, people are choosing to go to HBM, but they're very limited in capacity, and you can only put so many of these HBM stacks around that SoC on that silicon interposer before you run out of physical board space. And then, of course, storage on the lower right, we have a NAND die that maybe is 100 gigabytes. It's persistent, and NAND SSDs ranging up to 16 or 32, maybe terabytes today. So you can see this progression also of components being put together into subsystems, which are being put together in many of those into a system. The improvement of HBM brings us an extraordinary advantage in bandwidth, but at limited capacities. Next slide, please. Moving forward, we have some real opportunities in front of us. You're seeing introductions of all of these in the industry today. We're seeing opportunities where people are introducing near memory computing prototypes. We're seeing some prototypes and products in the computational storage arena. I've added energy to this slide, and this is kind of an important thing to note, is that just due to the long latency of NAND accesses, the energy tends to be pretty large to retrieve data from NAND. Not to mention the fact that you kind of have to access a fairly large amount of data in order to do the error correction required to retrieve that information reliably. So whereas storage accesses tend to be hundreds of picojoules to nanojoules, memory accesses tend to be in the single digit to maybe tens of picojoules to do accesses. Get that data into some place where you can do an operation on it and make use of that information. As we move compute closer and closer to memory, we get into the fraction of a picojoule per bit. And so, data movement on a DRAM die is frankly not very expensive compared to the overhead of bringing that data off of the DRAM die through a silicon interposer back up onto an ASIC where you do something different, additional with it. And the cost of the compute, frankly, is much less than a picojoule as well. So tightly coupled memory and logic can enable in-memory compute, near-memory compute, and in some cases, people are looking at analog compute, which is reusing a memory arrays to do very, very interesting but function-specific operations. We have emerging standards like CXL that really improve the viability of these sorts of accelerators. So the future, I think, is fueled by this reduced energy and increased bandwidth, and to some degree enabled by near memory compute. Next slide, please. Just a word on the CXL interface. I don't mean this to be so CXL specific, although the CXL is the one standard that's starting to gain traction in the industry. This really changes the game with regard to in-memory compute and, in fact, emerging memories, because in order to sit on the DRAM bus as shown on the right side on a DRAM DIMM, first of all, the cache line is striped across many DRAM dies, so no one die has the context to do any meaningful compute, unless you go to extraordinary lengths to reorder the data such that it does sit on one die. Additionally, there are very strict access latency constraints to operate on that DIMM. And so without changing the whole ecosystem, it's very, very difficult to put emerging memories into existing sockets. Whereas on the left, in a CXL interface, you actually can mix and match memory technologies. You can have tiering artifacts on that. You can have accelerators on that. And because the CXL interface is a transaction-oriented interface and enables cache coherence, that accelerator to participate in the cache coherence schemes of the system, that lowers the bar for both in-memory compute, all kinds of accelerators, the mix of many heterogeneous memory types on the same subsystem. It's a very big enabler for those sorts of things. Next slide, please. So one thing that we need to recognize is there is a corollary to Amdahl's laws. When these compute kernels are optimized, absolutely something else will limit our performance. And that something else most times is memory bandwidth, but sometimes it's storage bandwidth and sometimes it's network bandwidth. In some cases, in fact, memory capacity can be used to overcome storage and network bandwidth challenges. For example, you can increase your memory capacity to reduce the storage bandwidth just by storage caching. In fact, that's done commonly in operating systems today. Similarly, increasing storage capacity to just store data locally rather than always retrieve it from the network is a trade-off that can be made. I think all of these things are kind of squeezing a bubble in optimizing the overall system, whatever that system may be. But the move to domain-specific accelerators always is going to replace new and increased demands on the memory subsystems, and many times that comes to memory bandwidth. And next slide, please. So in summary, we have some big industry challenges ahead of us. Memory and storage demand in data centers is expected to continue to grow, and there's no question that scaling is both slowing, but also becoming in many ways more expensive. But I've been in the memory industry for 30 years now, and one thing that I will note is that the end of scaling has always been imminent since the very beginning of my career. So I think that the industry continues to fund research that leads to large innovation in the scaling of these technologies. And I'm pretty sure that's going to continue as we move forward in one form or another. One thing we have to recognize is that the suppliers really have to invest a lot in getting new technology off the ground, and there's a lot of risk associated with developing these new technologies because there's no guarantee from the beginning that people are going to buy that technology. And the development cost associated with the first generation of each new technology is enormous. And the end customers in many cases, they want to sample the first generation. They really don't go into production in any meaningful way in the second. And then they want to go into production in the third, which is, it's really difficult to fund 3 generations of technology development on something that may eventually become a reality. Also, business and ecosystem challenges are really as big as the technological challenges here. The human resources is a big deal. Programmers, people have been buying extra compute hardware for years to make it easier and simpler for their programmers. Now we're moving into this domain-specific architecture generation, and specialized hardware engineers are going to be very important moving forward. Whether it's general or special purpose hardware, there are challenges associated with both of those. On the one hand, you'd really like to have a general purpose CPU to fill your data center, because then you can just switch your inference engines to your web servers, right? But I think in many cases that's not the case now. That people are moving to very specialized functional hardware. And then new models are really emerging. The new standards, we talked about CXL a little bit, but I think moving forward, compute near data is going to happen, and really it's a question of specifically how does that happen. The advantage is there, the opportunity there is just way too large for it to not take traction, and I think pretty soon. So with that, I think that's the end of my presentation, and I will turn it over to Heike to lead the panel discussion.
Thank you very much, Sean, for giving us this excellent insight and introduction into the discussion today. I really appreciate. My name is Heike Riel. I'm a fellow at IBM, head of science and technology, and lead of IBM Quantum Europe and Africa. It's a great pleasure to lead us through today's panel discussion. And actually also Sean will join us for the panel discussion. And here we have more time than to discuss in more detail the insights of the Decadal Plan for semiconductors, and in particular, of course, the new trajectories for memory and storage. There is an amazing amount of data which we handle to store, to save, and find new ways and new innovative ways and solutions for this. So I'm really very much looking forward to the discussion. We have excellent panelists who are joining us today. Distinguished experts in this field will participate in the discussion. So David Pellerin from Amazon is joining. He is actually a head of the worldwide business development for Infotech Semiconductor Amazon Web Services. And he is focusing on high performance computing applications and on the semiconductor industry. We are also joining us is Caroline Duran. She is Vice President of Data Platforms Group, Engineering Manager, Memory and I/O Technologies from Intel. And she is responsible for broad scope, including pathfinding, architecture validation, and standards development. Then I have the pleasure also to introduce Stefan Helmholtz. He's Senior Vice President, Business Development for Data Storage at TIST Bioscience. And he's a very experienced industry expert in product technology as well as business development roles in semiconductor memory and data storage. And furthermore, I'm very happy to also be joined today by Jing Li. She is an Eduardo D. Glant Faculty Fellow and Associate Professor of Electrical and Systems Engineering and of Computer and Information Science at the University of Pennsylvania. And last but definitely not least, Jesse Mee is Acting Mission Lead for Pervasive Technologies and Lead for Space Electronics Technologies at AFRL Space Vehicles Directorate. He helps define the directorate-wide strategic vision and long-term goals for pervasive technologies and helps shape a portfolio of projects emphasizing game-changing spacecraft bus technologies and electronics. So very warm welcome to all of the panelists today. So we will now go into the panel discussion. This means we will start actually by a 5-minute keynote of every panelist. And then I would actually like to ask you to post the questions which you have already in the question and answer section. We will then answer them later in the discussion after the 5-minute panel presentations. So please, let us start with the first speaker and have David starting with the presentation entitled Application Drivers for Memory and Storage. David, it's yours. Take it over.
Thank you so much, Heike, and thank you for the other panelists as well. It's really been enjoyable to have these discussions leading up to this. I wanted to talk a bit about where we see the application space going and talk a bit about why cloud is beginning to drive a significant specialization as well as providing a general purpose platform for compute. And those two things sound like they're in opposition, but actually, if you think about the scale of cloud and our ability to optimize for specific applications, it just makes sense. So next slide, please. So first, let's think about the scale. You know, if you're a hyperscaler or a cloud provider, AWS, you know, we're global. We've got 25 regions, 81 availability zones, but more interestingly, we're now at the edge. And so there's significant technologies in support of edge devices, autonomous vehicles, sensors used in industrial, home automation, and so forth, where the boundary between edge compute and memory requirements, storage requirements, and cloud capabilities begins to blur quite a lot. And this is particularly true when you look at IoT and AI/ML, as I'll discuss in a moment. So next slide, please. But just to give some idea of scale, when AWS was launched back in 2006, it was really the S3 storage service, which is an object service. Simple queuing service was another service, and then EC2 instances, which came shortly thereafter. So think of that as a platform for deploying 3-tiered websites, simple databases, and so forth. But very quickly, with the availability of on-demand compute, we saw all kinds of interesting applications flowing into cloud. Genomics is a great example. So genomics and proteomics on the HPC side came in very early. But today, you've got a huge number of discrete applications, higher level services, AI/ML platforms, partner solutions, all of which need to be supported in this environment and supported in an energy efficient way, in a scalable way. When you think about scalability of the service today, I mean, S3 today, that's we're storing over 100 trillion objects, and those objects could be a few bytes or they could be multiple terabytes, those objects. And so we need to have strategies to fragment that data, to store it across many different devices. And just one data point there are tens of thousands of discrete customers on AWS today that their data is striped across or fragmented across 1 million or more different storage devices, each one of those customers, right? So that's the kind of scales we're talking about. And then the ability to handle transactions at scale, you know, perhaps 500 million API calls per second in the case of our identity and access management. The next slide, please. So we need to think about reliability. We need to think about power consumption. We need to think about application-specific accelerators in a very different way as we move from a kind of a generic virtualization platform of cloud into these highly specialized domain-specific areas and what we do out at the edge and in the rugged edge. Next slide, please. On the memory side, there's absolutely a trend now toward higher and higher ratios of memory to compute. If you look at EC2 instances that have been released over the years, if you look at applications such as in-memory analytics and machine learning training, and many others, stream processing, you do see the need for larger and larger amounts of memory and different memory hierarchies in support of different applications. Because again, what you do for streaming frame-based types of operations, such as video or LiDAR or other sensors, can be very different from what you do in large-scale data analytics. For example, running SAP HANA or Spark or applications such as that. And for many of the applications in the streaming domain, we have to think about alternative architectures that are heavily pipelined, that perhaps use different strategies for bit precision, for example, in AI/ML. And so we do have, because we have the scale, the ability to optimize for specific applications, or perhaps offer abstractions on top of our services, API-driven access to services that we can observe performance characteristics and then begin to optimize the stack underneath with alternative hardware, but not disrupt the application development. That's a really key idea behind abstraction, has been for many years. Abstract the details of the underlying hardware, allow the application developers to run fast with higher level tools, and then optimize underneath with alternative hardware. And next slide, please. On the storage side, I mean, because of the scale we have, again, we continue to innovate to the greatest extent possible. We abstract away the details of what we build down below, but we've announced recently that we do develop our own storage infrastructure. We have our own, custom FTLs. We buy NAND. We seek consistency across the storage platforms, as well as having perhaps different priorities around power versus resiliency. I mean, when you're operating at massive scales, you have components failing all the time, constantly. And so you need to build resiliency in, which creates different priority around power consumption, performance, reliability, and so forth. So next slide, please. So with that, I wanted to thank everyone again. I've gone a minute over, so I want to cut it off here, but we do have a lot of initiatives around sustainability if you're interested, and projects that are available on AWS and Amazon.com. Thank you very much.
Thank you very much, David. Really appreciate sharing your insights with us. So let's then move on and hand over to Carolyn.
Thank you very much, Heike. It's my pleasure to be here representing Intel. As Heike mentioned, I lead a memory and IO technologies team. So it was nice to hear Sean speak not only about the memory challenges, but also some opportunities that come from interfaces like CXL. In the few minutes I have together, if you don't mind going to the next slide, please. I want to maybe pull together the pieces we heard from Micron in terms of the challenges related to the memory that they're working on and developing, and we heard from AWS on the challenges they face as a user and customer as well as a creator. And so I wanted to step back a little bit and just take a look at the whole memory hierarchy. And so on the left, we have at the very top, you would think about this as SRAM, compute cache, very, very near to compute. There's a lot of activity in that space. And then moving down the hierarchy, traditionally, we had moved from SRAM to DRAM to storage. But over the last decade, we've seen quite a growth in the hierarchy driven by those demands that both the previous presenters spoke on. A key area right now in the hierarchy, and the one that I'll focus on today, is that space between the SRAM as we have known it in the past and the DRAM as we've known it in the past. It can be considered in-package memory, tightly coupled memory. As Sean described, there's a lot of innovations on taking existing memories like SRAM and DRAM and getting them closer together, compute in near memory, as well as stacked SRAM and things that we'll see along that, but also a space for new innovations in the types of memory that we can create there. The demand in this space is driven by needing more capacity than a traditional SRAM solution would provide, but also more bandwidth than a traditional DRAM solution would provide. And how do we decouple that bandwidth capacity ratio to drive, meet the needs of the customers? Our demand drivers in this particular space are typically artificial intelligence, machine and deep learning, and as well as the expansion of the edge and the network, as David had described. The key challenges are even higher. So there are ones, and Sean spoke very nicely about not only the technological challenges, but also the business and use cases. And one of those primary ones is the fragmentation of the use case. You can see as the technologies expanded and even accelerated adoption of technologies during COVID, we see use case fragmentations and different business models that don't fit neatly into this hierarchy as it has been. Additionally, on the physics space, we end up with hitting the power wall. And how can we continue to feed the beast, as Sean said, in terms of delivering to compute with memory as that ratio of needs of memory to compute continues to change. Tightly coupling them is one means by which we can solve that. Cost in general is also an impact of the limitations of scaling. And I know all of us as end user customers or companies like AWS are certainly focused on how we can deal with cost, not only the inherent cost of the product itself, but the use over time. So looking at power during consumption. And then, as I mentioned, the bandwidth's important, the capacity is important, but also that bandwidth to capacity ratio. So you can have great bandwidth, but you can't get enough capacity with it. It doesn't do you much good, and the reverse is also true. All of these have to be solved with understanding how the memory solution that one would provide integrates into the final product. Software enabling is a key part of that. Applications have been built, and as they continue, there's opportunities to provide new hierarchies. But if you take an existing software infrastructure and try to drop in a new memory hierarchy, that is a huge challenge that we need to overcome. On top of all that, with as the scaling has continued to lead to challenges in the physics and the technology, and as the fleet sizes, as David and has described, are growing huge, in which we can see those defects per million or defects per trillion in a fleet size the size of AWS, security and reliability are key functions there too. Next slide, please. With those challenges, though, are grand opportunities, and I'm excited to be here as part of the discussion on the Decadal Plan to understand what can we do to change the picture here. And so on the top left, I just show a slide that shows how bandwidth has been scaling for compute, which is the top part of the chart, versus interfaces, and Sean describes CXL, but you can think about PCIe or NVLink and others, and also memory, which are in blue and green respectively. So we need to, that gap is widening. We need to figure out what we can do to bring that back together. And tight coupling is one potential solution. And then on the bottom left, we show as a function of bandwidth, what happens to power for different memory standards that exist in the market and SRAM. And so you can see that that's increasing as a function of trying to drive that bandwidth as well, and leads to another grand challenge and opportunity. Now, for how to solve this, and that's what we look to this audience for, there are multiple ways in which to address the problem. So there's manufacturing device opportunities, what we can do with the existing memories, like shrinking SRAM, or in the bottom, improving or changing the way we look at DRAM. There are alternatives that are under exploration, as we all know. And then so much has happened with the way in which we can integrate compute and memory together in construction and integration package innovations that can help us unlock some of the opportunities that may have not been there for us before. So I'm excited about what's possible with 3D stacking and tightly coupling two disparate pieces of silicon together. And then in the middle, I'll just end with some of the architectural based opportunities that we cannot ignore either. So making the best use of those memories and logic that exist. And so we can look at process in or near memory. We can look at compression to make sure that every bit of data, that you're only moving what you need to move and when you need to move it. We can look at pooling opportunities to make the most use of the pieces of memory that exist so that each of them is being fully high utilization. That helps with not only cost, but power as well. Disaggregation to move the compute and memory where they need to be in smaller chunks than we're used to. And again, software optimization. And the DRAM improvements, Micron and others are certainly working on the next generations of all that we know, also focused on in or on package memories, and then, exploring what might be possible from a custom memory. This is definitely a space in which there is impending change. We are hitting walls left and right, and so it's ripe for innovation, ripe for new solutions, and I'm excited to see where we land. Thank you very much.
Thank you very much, Carolyn, for your presentation. Really great insights also. So let's then continue to the next speaker, and it's a pleasure to have Stefan Helmholtz with us.
Thank you, Heike. I very much appreciate for being on the panel. If you can advance the slide, please. So I want to switch gears from memory to storage. And as David was saying, we need to reinvent everything. I like to exemplify that in the coining of we need to scale up from thinking about data lakes to thinking about data oceans. This is probably a good analogy also to represent the SRC scaling goal of 100x or more growth in areal density capability. This is all warranted and supported by a very strong and healthy demand side, which on the left side chart, you can see the demand side through data being created. That is complemented on the right side with the demand for data storage shipped annually. So when you are looking into dimensions for a second, again, further exemplifying data lakes going to data oceans, the industry has shipped most recently roughly 1 zettabyte of storage, enterprise storage, and at an annual cadence. That is projected to grow to, at the low end, 12 to 15 zettabytes, and at the high end, the forecast range from 30 to 50 zettabytes. So that's an increase to the tune of 10x to 50x, if you just look at the range. Now, as experts have been looking at current storage technologies, they have concluded that the supply of data storage will not be able on its current trajectory to keep up with demand. And thus, the conclusion is that we need new storage technologies to create a response to this emerging need for immense available capacity at minimal cost, as the SRC Decadal Plan calls for. One very important thing to note is, as we're looking into storage growth overall, archive storage is actually the fastest growing storage tier. And with that also represents evolving and new workloads. So you can clearly see that we have actually in the cold storage domain, when you look at bit growth, it has the highest CAGR across the entire bandwidth with regards to growth. If you can advance to the next slide. So then the question is, how do we address this growth, right? And it's not one or the other technology, but I think it's all of the technologies in concert. In addition, we also have to add new tools to the toolbox, as we previously concluded. And when you look at the potential candidates for scaling as a first order of magnitude problem solving, you can clearly see that DNA data storage is the ultimate answer for data scaling, data storage scaling as we look into the future. It is the ideal candidate not only because of the high density, but it also promises to be cost-effective, sustainable, and energy efficient for long-term data storage solutions. Again, see this as a complementary solution to the existing storage solutions that also will continue to scale. What is very important is, as we are looking into storage scaling, we need to understand, observe, and carefully evaluate how will workloads evolve and what new workloads do we have, and tailor for those workloads our storage solutions. We have clearly at this point in time limited longevity on current storage solutions, also compounded with the problem that they all require data migration. And when you think about the scale that David outlined, right, of operation and hyperscale, imagine you now have to migrate a growing pool of storage to new storage from time to time. So the more you can optimize that with new storage solutions that do not require data migration or require less data migration, you would have clearly something to be gained. The other part is that we need to look at archive storage also in the context of reinventing, as we need to address the capacity, access, energy, and cost needs that are at a different scale from where we are today if we look at the future growth outlook. Another thing that comes to play, also mentioned by others, is the energy and sustainability concerns that are on the rise. It's clearly foreseeable that we likely will have a storage carbon footprint per terabyte in a not so distant future. And as we're looking then into the last consideration as to not only do we need to store all of this data, but we need to also find a way, as Sean mentioned, to compute on it. And what is interesting to note is that there are actually opportunities to have computational storage solutions, not only in the hot and warm domain, but also in the cold domain. So DNA data storage, for example, offers the opportunity to have, whether it's search or inference operations being performed on the actual DNA data storage itself through biochemistry tools that are available today. And with that, we can look forward and are excited about the journey ahead of us to solving the challenges and service the opportunity in data storage growth. Thank you.
Thank you very much, Stefan, for this insight into the storage and very exciting new technology which is coming up. So let's then continue to Jing Li from UPenn.
Thanks, Heike, for the introduction, and thanks you all for the opportunities to speak with everybody today. I will talk mainly from academia's perspective on some of the fundamentals we think it would be good to research on related to the decadal challenges. Next slide, please. As you heard from the previous speakers and Sean's keynote, innovations are really needed to address these challenges. So first, we would like to use this push-pull example to highlight the concept I would like to introduce today, memory as a service. The general principle behind how we use memory for the past many decades is a memory as a device based on the push strategy. Our today's memory software hardware are designed to access data in memory hardware based on the anticipation of future demands, usually provisioned ahead of time by memory or processor vendors and cannot be easily changed after manufacturing. So the direct consequence of this is that we fetch a lot more data than actually needed and move a lot more data times than actually needed. So we may get high throughput, but low good put. By definition, what I mean by good put here is the amount of meaningful data to the application transmitted instead of the total data transmitted per unit of time. We can also view it as application level throughput, not hardware level throughput that we generally use today. A simple example is this DRAM overfetching problem. Even if our application needs to access a single word of data for byte, we need to fetch a 1 kilobyte of DRAM row, regardless of what application is running. So more than 99% of data fetch are wasted. There are some research efforts in this domain, but still relatively far away from fundamentally addressing the problem due to the way we use memory. In current scenario, memory is designed to be a hardwired application agnostic. As a client to host the processor and computation, we can only implement the simple and fixed memory function load store. When we build the software on top of that, we abstract the memory using a decades-old simple abstraction, a location-based linear address space. In memory as a service, we envision memory can be designed and architected to be application-aware, programmable and customizable towards this application in the same way as a processor. Instead of serving as a client to computation, it can be truly the first-class citizen and the host of the data. We can implement a rich set of flexible memory functions beyond the load store, and we can add a rich set of new memory abstractions to help better reveal the logical relatedness of the data. And this will help us to realize the pull strategy. We can access only the useful data in the memory hardware based on the present demand of running applications, so that we can get both higher throughput and good put. This may help to extend the bandwidth scaling challenge illustrated in Sean's keynotes. And next slide, please. So if we put a memory as a service in the broader prospect, we already see the computer system is becoming more heterogeneous, including not only CPU, GPU, TPU, but also a rich set of domain-specific accelerators. Similar to the trend for computing device, the memory subsystem is also becoming more heterogeneous, including not only DRAM, but also HBM, non-volatile memory, or various computing memory, computing storage devices. A future system is likely to contain a combination of all these compute and memory devices, mix and match. And if we really want to use these devices really well to get the best system performance, we need to optimize them. For each computing device, we need to optimize its memory subsystem separately. If we consider another dimension application, it would be very hard to scale. As the design space is huge, the optimization complexity is O(n) squared. And this significantly increases the deployment barrier for entry of any new memory devices into the system. In memory as a service, what we need is a service layer, which can help to realize the vision we just discussed. The service layer enables an ecosystem that is really built specifically centered around memory instead of compute. It contains hardware software components, provide the interface to plug any new memory technologies into, as well as provide programming models to make programmers' life easier while helping to decouple the optimization between compute and memory, reducing the optimization complexity from O(n) squared to O(n). Here, I list a few key enabling techniques that may help us to get there. First, the software-defined memory, a technique and vision that we proposed and published in this year's S+ by my students Jialiang Zhang. The idea is to make the memory subsystem software-defined instead of hardwired, so that we expose memory system directly to application through a service layer, not through the compute device. This allows users to better control the customization of the memory hierarchy tailored to their own applications for higher output. Another is advanced interconnect. When we build various types of hardware, we would like to have a modular and easy integration of these devices into the system, plug in and play. We have already seen a good industry effort, such as the Computer Express Link CXL mentioned in Xiang's keynote and also Caroline's talk. So it allows us to scale compute and memory independently. Finally, new standardization and consortium. Ideally, we would like to define common grid high-level protocols and software interface, allow us to support more advanced data operation to the users across application they need. To make all this possible, we really wanted to have the close and active collaboration across the system stack and between industry and academia. Thanks. That's all I have.
Thank you very much, Jane. That was really a good complementary presentation to what has been said before. So thank you very much. Very, very interesting. And we will continue with Jesse Me. And I would like to, before Jesse starts, I would like to encourage also the audience again, please use the question and answer button or interface to already raise your questions, which we then can discuss in the panel. And if you are not talking, please go on mute. We will continue now with Jesse from AFRL, talking about AFRL space electronic technology.
Hi there, Heike, and thank you for the introduction and the other panelists. So I'm going to be talking about the developments and I guess applications and challenges of memories in a little bit different domain, obviously for the U.S. Space Force, and we're working for space technologies. So I run a pervasive technology portfolio, which kind of spans the gap from guidance, navigation, and technology, thermal management, structures, power, and of course, space electronics. So the things that are used kind of ubiquitously across our architecture. So if we go to the next slide, I want to talk obviously about space electronics. That's most relevant for this discussion today. And kind of the vision for the program out at the labs is to develop the resilient space electronics to enable our next generation capabilities for our satellites and our strategic systems. And we approach this kind of in three paths. We start with basically what are the high risk but potentially high payoff types of investments that we can make in our electronics technologies. And so that's kind of the far left there. Things like analog neuromorphic computing, and you'll hear about some advanced memory concepts. So in fact, Stefan just talked about the DNA memory. That's the kind of thing that we would explore within this area of the portfolio. The idea is that those would hopefully transition into more applications activities. So if you look at the center, it's really where the pedigree of the program out at the labs is. It's, developing and transitioning to, for use in our space system. So things like rad-hard processors, rad-hard memories, and everything in between. And then finally, as we heard a little bit about from Micron earlier, there's a lot of challenges with, understanding mission codes with computing architectures and the way that you use the memories and the way that you use the processors. And so we have a strong effort in assessing and validating electronics for their performance. So how well, what's the extent to the level which we can parallelize an application, or, how do we get limited by memory bandwidth within our processing chain? So there's sort of the performance, and then of course the radiation susceptibility, understanding the limitations of the hardware that is appropriate for our mission, the limitations of that hardware within the radiation environments that we want to put them in. And so if you advance once, it should just build out basically the touch points for advanced memories within the electronics program. In many ways kind of falls within these first two buckets. And so currently we're working on the exploratory research side, we're working on some memristor crossbar array development, either for dense memory or for, you can use these for analog types of compute applications. We're also looking at magnetic graphing memory as a good rad-hard memory. And then more on the applied side, we've really got three key memory investment or memory activities right now. There's an SRAM-based DDR3 that we're working on. There's a spin transfer torque MRAM that we're doing. We're also doing a Sonos-based NAND flash within the group. And so if you go to the next slide, what I wanted to do was motivate some of the drivers within space for doing more processing than we've done in the past, and more. And of course, the processing architecture necessitates increased memory. So one of the challenges that we're dealing with is, of course, the advanced sensors that are being developed and deployed. Those produce a lot of data, and it's actually overwhelming the communication bandwidth off of the spacecraft, meaning that we need to do more with processing. And so we talked a little bit about, there was on a slide about the computational storage and pulling that memory closer to the sensors, pulling the compute closer to the memory. We're trying to reduce the amount of times we move the data. We're trying to get to a point where we're not sending raw data, but we're sending processed information around. So there's some other challenges, as we look ahead toward constellations and what we would call like proliferated LEO. There's things like Space Development Agency and DARPA, and obviously SpaceX and their constellations. There's a lot of satellites going up now, and we're trying to figure out on the government side how to leverage this kind of architecture. That, of course, necessitates a lot of movement of data between the satellites through communication links, but increased processing and memory on board. And then there's a lot of opportunities to leverage advanced data processing techniques. We talk a lot about AI, ML, and understanding applications for these technologies within our space systems. And so we do a lot of work in that area. What I want to do in this last slide is just kind of talk about some of the specific challenges that we face within the space electronics community. So obviously we're deploying these technologies into a pretty harsh environment. And the consequence of trying to create purpose-built radiation-hardened technologies is that we end up with this kind of sizable gap between our state-of-the-art, state-of-the-practice, space-based technologies and where commercial is going. So obviously we're just kind of showing the Moore's Law scaling trend of various technologies over those several decades, and kind of the blue, green, and yellow line, you can see how technologies evolve. The orange line here just tracks the scaling trend of our advanced space-based technologies. And what you'd find is there's about a 10-year gap between our current rad-hard capabilities, which we're developing, and where we live in the commercial. And in order to do a lot of the missions that we want to do in the future, we're really trying to explore how do we close that gap? Are there mechanisms through which we can learn to leverage commercial technologies within a space environment, or are there mechanisms through which we can accelerate the timeline that it takes us to develop rad-hard technologies for space? And with that, I'll leave it there and turn it back over.
Yeah, so thank you very much to all the panelists and also to Sean at the beginning to introduce a lot of information and to give more further insights into the Decadal Plan, but also the specific thoughts and challenges and opportunities which you see. So we have now time for discussion. And what I've seen actually is that, of course, everyone talked about application and it's getting more application specific. And, and we touched upon, just about space, which is a very specific one, of course, but then there is cloud, there is IoT, there is AI, there is the combination with the logic. So this is really, it looks to me like we are going from something which was very systematic and we knew exactly what we needed to do to something where are a lot of opportunities, but there is almost no roadmap anymore because it depends very much on the specific application, what you need to do. And so I wonder, what does it mean for you, right? Because what applications will, the application will drive new memory and storage technologies. But on the other hand, also cost is important, right? Cost and time. And so how do you balance this? So what is most important for your area? And I don't know, but perhaps, Carolyn, you may want to start in this because
Sure.
You pointed this out also very much with the applications.
Yeah, and I think there's a question in the Q&A that's similar in terms of knocking down the memory hierarchy and rebuilding it. And I might flip that around. I think what we're seeing is a diverging. So we'll have some areas of need which will be highly specified, and we'll have some embedded type of very near compute and logic together. And then for the rest, we would want modularity. So rather than trying to keep the hierarchy to 3 levels or whichever levels you want to pick, how can we use integration and construction to make late binding decisions to serve the needs of the customers best, and then right size that compute and memory and together late in the process. So you have the tools in the toolbox, but you can integrate them in different ways. Now that's a nice, simple answer. How we go about making that happen is wherein all the challenge lies right now. And so I think we're all in that space of trying to figure it out.
So what do you take as certain criteria for? Because I assume you need to pick what is the highest application for you, where you can, in the end, you also can get, the investment back and all this. So what is it where you look most into it?
Well, and I see there's others that want to contribute, so I don't want to take too much of the time. But for us, we're in a relatively unique position because unlike David, where he's designing for his own product, we have a balance between multiple customers with different all their different use cases and applications as well. And so we have to take it by the solving for the most. And then you'll see also in compute as well as memory, a diverging and some more of that purpose-built solutions. And so that's again where modularity becomes key. We can find commonalities in the tools in the toolbox, but if we can only put them together in one fixed way, that's where we lose the applications. Where if we can take a piece of A and a piece of B and put it together, I can solve problem A for customer A, and I can do a different solution for B without having to invest all of the things over and over again. I also think Jane's point on software enabling is huge. So if you could take the pieces and utilize them in different ways, that can also help. I'll turn it to another panel member.
Yeah, exactly. So let's have David, because I think for David, it's also a big thing, right? You have so many different applications also driven on your tools.
Yeah, that's right. And you think about the history of application-specific accelerators, and we saw them for years in DSP, signal processing, genomics, the use of FPGAs and crypto. And it's important that we enable that and that we work to create application-specific accelerators, but also at the same time provide abstraction layers so that applications don't become completely wound around the architecture of a particular generation of accelerator. FPGAs, always a good example of that. So an example of this in AWS is, we have our Trainium and Inferentia custom silicon chips, but it was very, very important for us to also develop frameworks and compilers and so forth on top of those to create abstraction layers so that, as these applications evolve and the ability to optimize for those applications evolves, we can quickly pivot and, to the greatest extent possible, abstract the details of that actual hardware.
Thank you. Jesse, you also talked about very specific applications. Perhaps you may want to add your perspective.
Yeah, actually, I just heard something that was really important, which is keeping the cost down. And one of the challenges that we face in space is, of course, trying to develop technologies for these challenging domains while keeping costs down. And that's becoming more important now than ever before. It used to be we would develop a few very large and also very expensive satellites, but this kind of pivot toward a more disaggregated architecture and more satellites in lower Earth orbit, and that pivot necessitates that we get the cost way down, because we can't afford to create the number of satellites at the scale that we want to do for the future architecture at the price points of our old architecture. So I just wanted to say that that's certainly something we're addressing.
And actually, I would like to ask this same question also to Jane, because Jane, you also had this, specific but also agnostic, and I wonder also in your perspective, what does it mean?
Yes. So if you look at the history of a computer device, we start from the general purpose processors, and it's fully programmable, agnostic to applications. We can essentially program it to run anything. But if you look at it from the memory domains, we are in the point of, so memory, we have a very limited control to customize it towards applications. Anything we do is very limited. We have to do through the operating system, place the data based on the granularity of the pages. So this really gives us a very limited flexibility. So what I wanted to add here is, maybe, if we can really think, in different ways of, if we can somehow make the memory programmable and software defined, this could help us to change the trade-off and, the tight, between the programmability, the application agnostic versus a device driven, so that, can better address this problem.
Okay, so actually, I also, Stefan, you have a very specific, you talked about a very specific storage application or device, right? So perhaps you can also add your perspective on where do you see the DNA memory specifically applied to? What is the advantage and how do you want to apply it? What are your roadmap kind of applications for this?
Yes. Clearly, DNA data storage is expected to emerge from the cold, right? So bottoms up, if you look at the storage pyramid. And as such, you have basically everything in there from a storage offering, starting with the deep archive and then going into an accessible archive. What is very important for us is the opportunity to actually have indication of the data temperature that will help us to determine what data should go on which storage device.
Okay, excellent. So there was actually let me ask one specific question Jeffrey has. What is the role impact of embedded NV memory for cache or other applications? And how would it change if NV memory performance and endurance could match embedded SRAM? Who may want to answer this question? Jean, is the question for you?
Yeah, sure. I'll take a stab at it. So first, the concept of non-volatile memory for cache is certainly that's excellent from the standpoint of being able to have really low power systems. But if we're talking about the non-volatile memories that exist in the marketplace today, the performance of those is far inferior to that you would get with SRAM, right? And so I think, and there was another question in the Q&A that came up earlier about embedded memory. So SRAM, we shouldn't ignore SRAM by any stretch of the imagination. That is a very, very important part of the computer hierarchy. But in the same way as I said that memory can be used to offset the requirements of storage in some cases, that leverages the locality of the workload, and the same is true of SRAM offsetting the need for memory bandwidth from DRAM, right? It's taking advantage of the locality of the workload to keep what you need handy so that you can use it again next time. And if your workload involves, just scanning through a lot of data, like petabytes of data, no amount of SRAM on the planet is going to save you, right?
Good. No, thank you, Jean. There is another question, actually. I find it very interesting because we discuss a lot, and there's a lot of also publications and papers and research going on emerging memories. And so the question is the industry picking up on these emerging memories, or is it becoming disillusioned with emerging memory technologies?
I could take a stab at that. I think this is the space where it's going to pop out. Like for the part of the hierarchy that I spoke about, that's where a lot of these emerging memories are being investigated. Some of the problems or challenges that come up as, understanding that workload, endurance, reliability, those kind of things. Typically, if you look back at history, and Sean can probably speak to this better than I even, it takes about a decade to bring a new memory, a brand new kind of memory into fruition. I think that the understanding what those opportunities are, and then addressing the investment and business needs that Sean also described to invest, multiple generations before the uptick from the industry are important. What I think will help those be successful is the disaggregation again, and finding ways in which we can do that. Now, of course, any kind of disaggregation adds latency and things like, and power to some extent. So finding that balance is going to be important, but I think we're at a point here where something's going to happen in this space, in my opinion.
John, do you want to comment also on it?
Well, I think, I personally have spent about 20 years of my career trying to get 3D XPoint off the ground, both as an Intel employee and as a Micron employee. And honestly, everybody knows that Micron pulled out of the investment that we had in 3D XPoint. I'm not going to say that that's necessarily a fault of the technology. The technology works, and it works real well, right? The problem is that it's squeezed between the economics of DRAM and what it can do, and the economics of NAND and what it can do, and there are very few applications that will kind of live. Well, maybe there aren't very few, but most of the industry's applications have been forced into either the NAND bucket or the DRAM bucket, right? And so finding applications in that Goldilocks zone is a real challenge. Even what I said about the persistence not really being a characteristic that people associate with memory technologies. It's more of a storage technology that people associate. So I think let me offer maybe an analogy. What has happened over my career with non-volatile storage is I worked on EEPROM, and then I worked on NOR flash, and NOR flash is EEPROM that you can erase, right? And in fact, it was an artifact of EEPROM that brought us flash. And NAND flash is a much lower cost structure. What really enabled NAND was the admission that we could let the system go manage some of the bad areas in the device, and then a very low cost structure manufacturing and design architecture for that technology. So we've had the entire history of non-volatile memories is really based on one technology that morphed over time. And I think maybe that's in some ways that's what we see with other memory types moving forward. For at least that's one path, right? Where maybe it's DRAM, maybe it's a variant of DRAM, maybe it's a variant of DRAM with with different interfaces, like I showed on HBM, right? And so I think that the industry is going to be very dynamic moving forward in that regard.
So I have a quick question to that, Jean, to you, because now with memory and logic coming closer together with the in-memory, isn't this also like a possibility, an opportunity for bringing this further into use?
Absolutely. So we've spent a lot of time working with researchers in the SRC program, the JUMP program, and there's a whole center that's focused on in-memory compute. And And what I'll say is many of the new memory technologies use higher performance logic, and oftentimes we're moving in the direction of lower temperature processing, which enables us to put better performance logic there. Also, the 3D stacking and those kinds of things are becoming a reality today, right? So, we're seeing in the industry stacked SRAM. AMD is doing a stacked SRAM as part of their architecture. We're seeing the Apple M1, the new MacBook Pros. They have, believe it or not, on the MacBook Pros, they have triple the memory bandwidth that you can get on a 2-socket server. Now, the price is only about half of what the 2-socket server would be, but right, the systems are evolving to take advantage of these new technologies that don't involve, brand new underlying memory technologies, and I think we're realizing some of those benefits even today.
So Jesse, I think this is since you mentioned some of these technologies right in your presentation. So can you also comment on this of how you see like advantages in your application area?
Yeah, I can talk a little bit about it. One of the areas specifically that we investigate a lot in space is MRAM, because the back-end line, the MRAM bit cell is impervious to radiation. A lot of the failure mechanisms that we see in traditional CMOS memory don't exist on the MRAM bit cell, and it has the properties that it can be kind of fast like a volatile memory, but persistent like a non-vol. And so we are exploring the advantages of that and weighing it with the cons, with potentially, they're sensitive to external magnetic fields, so you have to have some, sensitive shielding. But it's certainly an area that we're investigating. But I'll say that space typically follows commercial. So, I mean, you guys are certainly with emerging memories. Commercial is going to be at the bleeding edge, and then space is going to hopefully catch up. To give you an idea of scale, right now, the state-of-the-art rad-hard memories that we're investigating in, we're talking about monolithic densities in kind of the 512 megabit to 1 gigabit range. So if you're familiar with the state-of-the-art for commercial monolithic densities, you can see that we're significantly behind. So I think where commercial goes, especially if applications are if there's a strong utility demonstrated on the commercial sector, and we can see the clear advantages to deploying that technology within the space, then we will follow. We'll try to figure out how to make it hardened.
Thank you. Let me now switch a bit to also the new systems architectures and also the energy efficiency, right? Because this is really, I assume that in the future this will be becoming really a key driver. And so I wonder, actually, David, that may be a question for you, because I think you have a lot of compute and memory and systems which need a lot of energy. So how do you see that? Where do you see that there is the most effect in optimizing the system architecture to get also more energy efficiency? And what do you see as the energy performance capacity trade-off?
Yeah, well, it's incredibly important to our customers and to AWS to drive the efficiency up. I mean, you think about our goals for renewables, right? Powering the entire fleet 2025 and carbon neutral by 2040. These require us to do substantial re-engineering, and just an example of that. We do silicon design in part because it can drive down the cost of compute and storage substantially. Our Graviton 2 instances, for example, these are server chips that are substantially lower power than previous generation chips. And also in our training and inference chips, Trainium and Inferentia, a major goal there is to drive down power consumption for AI applications. And you find that throughout the fleet. I would say that it's one of our highest priorities right now because of the sustainability initiatives and zero carbon initiatives over time to really focus on power equal to performance, right? And if we have to give up component reliability to get there, we will, because we can build in resiliency at the system level. And that's a super important idea for us. Build in resilience at the system level so that we can focus on efficiency at component level.
Thank you, David. Jane, perhaps that may be also a question for you, the system architecture point of view, and where do you see the energy efficiency, and how do best optimize this?
I think as I mentioned in my previous talk, I think for energy efficiency, on one hand, we talk about from the hardware perspective and technology perspective. On the other hand, I think maybe we need a different set of metrics. For example, one example could be the good put, which is amount of meaningful data to the application instead of the overall data transmitted. So we have, once we scale the bandwidth, we scale the capacity. So another question is, how much utilization we can actually get from that. So if we can, a better utilization could help us to extend the system scaling roadmap. So I think, maybe a new matrix will be interesting to quantify this.
Thank you very much. So actually we have only 5 minutes left. And so I wanted to actually take a final question, which I ask to every panel member. And I thought what would be a good question is to go, what do you see as the picture of the memory and the storage in 10 years? What is it what you would like to see in 10 years of storage and memory? What is your kind of vision, and what do you think is also on the realistic scale? So what it would be your dream, and what is it what you definitely expect? So who wants to get started? Who's ready?
Actually, I can start. So I love Jane's vision of the future, right? We don't, energy efficiency, we can look at materials, that's an important aspect. But when we look at the, I'll just say, waste of moving data that we don't need, or grabbing data that we don't need, if we can, very exquisitely, like a surgeon, pull exactly what we need only when we need it, only use that energy when we need it, make it the fastest path there possible, like that would be the ideal state. And so I think we're all working towards that in different ways. There's the software abstraction, there's the proximity that we're looking at, there's new memory opportunities, but that's what I would see.
Thank you very much, Carolyn. David, you were nodding, so would you?
Yeah, I can. Also reflecting back to what Jane had said about memory abstraction, right? And abstraction. The compute and storage memory has innovated fast because we abstract, to the greatest extent possible, application development from the underlying hardware. And the more that we can do that, the faster they can both move. They don't become intertwined, interdependent. And so whether that is compiler technologies or virtualization technologies or higher level application layers with only API interfaces, finding ways to allow the hardware developers to move fast without having tripping up the application side and vice versa is really, really important. So keeping that abstraction in place is what's going to enable us to move fast through 10 years from now and beyond.
Thank you, David. Jean, do you want to continue?
Yeah, I like this, where this discussion is going. So if you look at the if you look to the past a little bit to look to the future, the x86 architecture in servers has been this architecture where we activate many more bits than we will ever use, unless your workload is just streaming. And then if that's the case, then why not just stream from storage, right? I really liked Jing's a picture of a new view of that architecture. And if I look to the past, I see that in the mobile architecture, right? The mobile architecture doesn't stripe across, for the most part, across large numbers of memory chips to get a cache line. They grab that cache line out of a device. And I think that as we move forward, probably our data centers are going to look much more like a smartphone of today, right? Lots of heterogeneous accelerators, a general purpose memory interface, but one that is conducive to all of those accelerators, right? So whatever the interface is, it should be able to provide very, very high bandwidth and very surgical access to the data that is stored within that. As well as storage interfaces, you know, when the Amdahl's law again, when we accelerate away the compute, we now fall on memory constraints. When we accelerate away the memory constraints, now that's going to put more pressure on the storage and network, right? So it's got to, we've got to bring the storage and network, and absolutely capacity is a really big deal that we need to bring forward in that as well.
Great thoughts. Stefan, what are you thinking about?
Sure. I will continue the virtualization and the abstraction path, right? And I'm saying that in order to utilize the underlying hardware, whatever it's developed, right, best, it would be very helpful to have an idea of a service level agreement, right? For every chunk of data that is provided, right, to the storage layer, because then the storage layer can decide how can I best service the need, the storage need, right? And it would also be abstracted from whatever you want to store it on, right? And today, let's start with that, right? Many people do not have an understanding of what's the temperature profile across their data. So even today, many people don't know what is the ideal storage device for my storage needs, right? It's just rather bulked in many cases, which is suboptimal from a cost and from an energy perspective. If we focus on that, I think we can get some more efficiency and a better cost structure.
Thank you. Jesse, in space, how is it there?
Yeah, I mean, if I had to look 10 years ahead, I imagine a lot more computational storage, a lot of processing and memory closer to the sensor to reduce just the amount of data that we have to operate on. Potentially data centers in space. We've talked about ideas about, you know, clusters in space and some different kind of far out there ideas. Maybe we'll start to realize some of those. Ultimately, I think it's going to be a hybrid, though, of purpose-built, radiation-hardened memories, working, you know, in concert with commercial memories that have, you know, corrective codings and redundancy, you know, to provide access to higher performance memory while still maintaining the reliability that we require in space.
Thank you. And last but not least, Jane.
Thanks, Xiang and David and Caroline. So I think I already mentioned my dream in my talk, memory as a service. As a person who work on memory technology for many years, and I spend more time to figure out how to make a better use of memory. So you know, also from the educational perspective, I would like to really promote the importance of memory and storage in our computer architecture classes. It's not the peripheral; it should be just as important, if no more, than processor.
Thank you very much. That was really great insight and great words to finalize our discussion today. I thank you all, the keynote speaker, the panelists, for the very exciting discussions, and of course also the great questions which have been asked. So everyone who listened to us, we learned there are big challenges, but this means there are also big opportunities. There are many applications, and I see there is a lot of work ahead. So thank you very much again. The questions which are not answered, the slides, and also the recording will be placed at the website where the event was, you know, it's described. So thank you again, everyone, for listening, and have a good morning, a good afternoon, or a good day wherever you are. Thank you.
Thank you. Thank you so much, everyone.
Thank you.
Thank you.